This video is a continuation of vectors. Before this, we talked about the dot product. So today, we're going to talk about what's called the cross product, which is another operation with vectors. Before, though, we jump into what is a cross product and how do you find it, we need to do a quick review of matrices, and that's how to calculate the determinant. So if you remember, the determinant is a numeric measure from a matrix. In a 2x2 matrix, like the one we have, you're going to multiply on the diagonal and subtract the other diagonal. So being careful here, -5 and -2 gives us +10. So when we subtract, we get -14. Make the determinant of a 2x2 matrix pretty easy to calculate, but the determinant of a 3x3 matrix is a little bit harder. So what you're going to do when you have a 3x3 is you pick one row, and each of those numbers becomes the coefficient on another matrix. And then the next thing that you need to know is your signs are going to change. So the 3 is positive, I'm going to change the middle one, and then I'm going to keep the last one the same. So then the way to figure out the other matrix, what goes in these matrices here, is for that 3, I'm going to ignore the row and the column that 3 is in. So I'm going to ignore this one and this one. And I'm left with -2, 5, -1, and 0. So then for that -1, it's going to be a similar idea. This time, ignoring the row and column that -1 is in, leaving me with 2, 5, 4, and 0. So the numbers here. And then for that 4, lastly, ignoring the row and column and being left with this matrix, which is 2, -2, 4, and -1. And now we have 4 mini determinants to calculate. So I have 3, and then diagonal, diagonal, so 0 subtract -5. This here gives us a +1, and again we get 0 subtract 20, and then we get 4 times -2 subtract -8. So this is 3 times 5, add 1 times -20, add 4, multiplied by 6. So 15, subtract 20, add 24, which gives us a value of 19. When you've done these before, you may have used a calculator. We will not have a calculator to calculate determinants, and so it's very important that we understand and are comfortable with calculating these determinants, and you'll see why in a little bit. Now, one thing I want to review real quick is what you can see in the box, is I told us to calculate these determinants, but you should have known that that's what you were looking for before I told you, and it's how. With notation. Anytime you see straight up vertical bars, that means find the determinant. Instead, if it's just a regular matrix, you're going to see brackets. So the fact that these up here just had vertical bars is how you knew to find the determinant. Now, that should have been a review. If it's not, that's okay. We're going to go through some more with calculating determinants. But 2 points to remember. If you ever have a matrix where 2 rows are the same, the determinant is automatically 0. Secondly, if we interchange 2 rows in a matrix, it's going to multiply the determinant by -1. So if we interchange 2 rows, it's going to multiply the determinant by -1. And that can sometimes be helpful. So you should be asking yourself, why do I care about this? And that's because of what we're learning today, which is called the cross product. So if we have 2 matrices, or 2 vectors, rather, in this case, vector A and vector B in 3 space, then if we cross those vectors, we get this complicated vector. But really what it means is it's the determinant of the matrix where we use I, J, K, and have our 2 vectors. What I want us to notice is that A cross B gives us another vector. So this is different from when we did the dot product. When we did the dot product, we dotted 2 vectors, we got a number. That's not the case here. When we cross 2 vectors, we're going to get another vector. So let's just look at an example and see practically how this calculation works. We have this vector u and this vector v, and we are finding u cross v. Okay, so the first thing I'm going to do is I'm going to set up my determinant. It's always going to have ijk. I then have vector u and vector v. So I'm going to choose this first row. So I have I, and then if I ignore the row in the column that I is in, I get 2, -2, 0, 1. Remember, we flip the sign. If I ignore the row and column that j is in, I get 1, -2, 3, 1. And then for k, I'm going to get 1, 2, 3, 0. Okay, so then I have I this way. I'm going to get 2, subtract 0. This way, I'm going to get 1, subtract -6. Add k, multiplied by 0, subtract 6. So ultimately, we find that u cross v then is 2i, subtract 7j, subtract 6k. So then what we want to know is what happens if we calculate instead v cross u? Are we going to get the same answer? Well, let's start by setting it up. We have our I, j, k. This time v is going to come first, and then u. Now, from the properties above, what we notice is all we did was flip 2 of the rows. When we do that, the determinant gets multiplied by -1. So what we're going to do is take our answer and multiply by -1, which means that v cross u is -2i, add 7j, add 6k. And that will always be the case. So what's important is that the order does matter. But when you switch the order, all that's going to do is switch the signs. Okay, so you should be asking yourself, why do I care about this cross product? And so we're going to review today, or talk about today, some applications and some properties, which is what we're going to look at next. Okay, here is what is important about the cross product. The cross product is going to be orthogonal to both vectors. Cross product is going to be orthogonal to both vectors, and you're going to use that. So that is going to be helpful, and it is something that's going to come up again. So if you are ever asked to find a vector orthogonal to both A and B, all you're going to do is use the cross product. Now, how do we find the direction? So if we have vectors A and B, how do we find the direction that the cross product would go in? And it's actually the right-hand rule again. So if you remember, we saw the right-hand rule in the first video when talking about the x, y, and z axes. So in this case, what you're going to do is you're going to take the fingers on your right hand and you're going to curl them in the direction of rotation, so less than 180 degrees from A to B. Your thumb then is going to point in the direction of the cross product. Okay, so let's move on. We're now going to look at some properties of the cross product. First property, you already know. If you cross 2 vectors and then reverse the order, all you're doing is switching the sign. So we saw that in example 1. Next thing you're going to see is if you have a constant, that constant can go anywhere. We can distribute a cross product. So if I have a cross product of a vector and the sum of another vector, I can distribute. Likewise, this direction. And then the ones that are a little bit less intuitive maybe are 5 and 6. So if I have a cross product and I'm dotting it with another vector, I can actually switch where that cross happens. But if I'm crossing 3 vectors, that I can't just switch whatever I want to. So those are some properties that you may find helpful later that are going to lead us to some of these fun facts below. First fun fact, the magnitude of the cross product is equal to the magnitude of A, the magnitude of B, and sine of theta. Now, what I want to remind us of is that the dot product is the magnitude of A times the magnitude of B times cosine of theta. So they're pretty similar. Another thing I want you to know is that A and B are parallel if and only if their cross product gives the 0 vector. And so the question should be, well, why is that? Looking above, if two vectors are parallel, then the angle between them is 180. So the sine of 180, or the sine of pi, gives us 0. So hence then, the magnitude of the cross product would be 0. And then, lastly, another fun fact is the magnitude of the cross product is equal to the area of the parallelogram determined by those two vectors. And that is something that we are going to look at in a little bit. Okay, so next thing we're going to look at is applying some of these ideas. We are going to find a vector perpendicular to the plane that passes through the points P, Q, and R. Okay, first thing that I'm going to do is I'm just going to draw myself a picture. Let's say that this is my plane, and remember a plane is determined by 3 points. Maybe you learned that in geometry, although I know that was a while ago. And let's say I have those 3 points. I am looking for a vector that is perpendicular to this plane. Well, what I notice that I can do is I can draw in these two vectors here, starting at P. So that's vector PQ and vector PR. And if I cross those, that vector will be perpendicular to the plane because it's perpendicular to PQ and QR. So what I need to do then is find PQ, find PR, and then cross them, and that'll give me a perpendicular vector. So PQ, I'm going to start with. So if we remember from earlier, we're going to have to do some subtraction. I'm ending at Q, starting at P. So that gives me the vector -3, 1, -7. And then PR, so this is the vector starting at P, heading towards R. So I'm going to have 1 subtract 1, -1 subtract 4, and 1 subtract 6. So this will give me 0, -5, -5. Okay, so I have my two vectors that make up the plane, but now I want a vector perpendicular to that plane. So what I'm going to do is I'm going to cross them. I'm going to take PQ, and I'm going to cross PR. So that's going to be I, J, K, -3, 1, -7, 0, -5, -5. So this is I times the matrix 1, -7, -5, -5. Subtract J. I have -3, -7, 0, -5. Add K. -3, 1, 0, -5. So then this gives me I multiplied by -5, subtract 35. Subtract J times 15 minus 0. Add K times 15, subtract 0. So that vector then ends up being -40I, subtract 15J, subtract 15, or add 15K. Okay, so that is a vector that's perpendicular to the plane. By no stretch is that the only vector that is perpendicular to the plane. Now, remember that scalar multiples of vectors are parallel. So what I can do is I can find any scalar multiple of this vector, and it will also be perpendicular. So if I wanted to divide this by -5, I would get 8I, add 3J, subtract 3K, and that is a vector that is also perpendicular to the plane. So this is pretty powerful, and it's going to be used in a few different ways, but that is the basic idea of the cross product. So let's go on and see one more application before we add on. Okay, so let's do one more application problem before we move on and build onto this cross product idea. So example number 3, find the area of the triangle determined by P1, P2, and P3. Okay, so if we picture what's going on, we have these 3 points, P1, P3, P2. So I can draw in this vector from P1 to P3, and I can draw in this vector from P1 to P2. Okay, before we just start jumping into some calculations, let's come up with a plan. If we have the vector from P1 to P2, and then we have the vector from P1 to P3, what we saw already, if we cross these vectors and find the magnitude, this will give us the area of the parallelogram. Okay, so if we can picture a little bit, that parallelogram would go like this. We just want the triangle though, so we can divide that in half. Okay, so we have a little bit of a plan now. We're going to have to find vector P1, P2, and then we're going to have to find P1, P3. So for P1, P2, it's ending at P2, so with my subtraction, I'm going to have -1 subtract 2, 0 subtract 2, and 2 subtract 0. So this will give me -3, -2, and 2. Similar idea, if you trust me, P1, P3 ends up being -2, 2, 3. So then I want to cross these. So this will give me my ijk, -2, 2, 3, -3, -2, 2. Okay, for time's sake, I'm just going to tell you what that vector ends up being. It's -10, 5, -10. Okay, what we care about though is the area of the parallelogram. So if we go back to the very beginning, we decided we needed to find the magnitude of this vector. Then it would give us the area of the parallelogram, which we then could use to find the area of the triangle. Okay, so let's find the magnitude then of this vector. When we do, we're going to get the square root of 100, add 25, add 100, which is the square root of 225, or 15. That's the parallelogram though. If we want the triangle, we're going to have to divide it in half. So the area of that triangle is 15 over 2. Okay, so we're going to move on. Next thing that we're going to talk about, which is related to cross product, is what is called the scalar triple product. So the scalar triple product of 3 vectors comes when we dot A with the cross of B and C. Or from the above properties, we can cross A and B and dot it with C. So the first question is this going to give us a vector or a scalar? Well, we already know B cross C is a vector. So we're taking a vector, dotting it with another vector. Dot product will give us a scalar. So this is going to be a scalar, not a vector. Now, another way to write this is we're finding the determinant of the matrix that has all 3 sets of components. Now, the question again that we should always ask is, why do we care? So why do we care what the scalar triple product is? Well, the absolute value of the scalar triple product is going to give the volume of the parallelepiped determined by those vectors. So first thing, notice what I said. These bars denote absolute value, not length, because we already said the scalar triple product is not a vector, it's a scalar. So this is absolute value, not length, and this is a parallelepiped. So it should look similar to like a rectangular prism maybe that you saw in geometry, but what you notice is it's not perpendicular to the ground, it's slanted. So the scalar triple product will help us find the volume of a figure similar to that. So here is a special application or a way that we can ask a question. Use the scalar triple product to show that A, B, and C are coplanar. Okay, so you might not initially know how to use the scalar triple product here, but you know you need to use it. So let's just start by calculating the scalar triple product. So we get A dot B cross C. So A is 1, 4, -7, B is 2, -1, 4, and C is 0, -9, 18. So this is going to give me 1 multiplied by -1, 4, -9, 18. Subtract 4 multiplied by 2, 4, 0, 18. Subtract 7 multiplied by 2, -1, 0, -9. Okay, so this is 1 multiplied by -18, subtract -36. Subtract 4 times 36 minus 0. Subtract 7 times -18 minus 0. And all of that ends up being 0. Okay, so the question is, what does that tell us? What that tells us is that the volume of the parallelepiped formed by those vectors is 0. That means they don't form a parallelepiped. The only way they wouldn't form a parallelepiped is if A, B, and C are coplanar. Coplanar meaning they're on the same plane. Okay, thanks for sticking with me. I know this has been a long video. We have one more application that we're going to do, and then we'll be done. Okay, so finally the last topic that we're going to talk about in this video is torque. So you can see at the top, torque measures the tendency of a body to rotate about the origin. The direction of the torque vector indicates the axis of rotation. And so here's our formula. The way we find torque is position crossed with force. So in the figure right here, you see R is the position of the wrench, and we are moving this wrench in the direction of force, hoping to tighten that bolt. So when we cross this direction by the force, we're going to end up with the torque vector. So let's take a look at two quick examples. Example 5, a bolt is tightened by applying a 40 Newton force to a 0.25 millimeter wrench as shown. Find the magnitude of the torque about the center of the bolt. Okay. One thing to note is that position has to be in meters. So if you have an example that has centimeters, for example, you're going to need to convert. Next thing is we are looking for the magnitude of the torque. So we're looking for the magnitude of T. I wrote that kind of funky. Magnitude of T, which will be the magnitude of R cross F. Okay, well, we don't have vectors for R and F, but what we do know is that this is going to be the same as the magnitude of R multiplied by the magnitude of F times sine of theta. Okay, well, the magnitude of that position is 0.25. The magnitude of the force is 40. Angle is 75 degrees. So the magnitude then of the, of the torque is about 9.66 Newton meters. Okay, and then finally our last example. The figure shows a force of 100 newtons applied in the positive z direction at the point Q. Assuming the cube is free to rotate about P, find the scalar moment, which is just another term for torque, of the force about P. Okay, so again, torque is going to be R cross F. F we can already see. So that F is the vector 0, 0, 100. The position then, if we're rotating about P, is going to be this vector right here. So that's going to be our R. So our R is the vector PQ, which is the vector 1, 1, 1. So what we're looking then for this torque is we are going to take that 1, 1, 1, and we are going to cross it with 0, 0, 100. So we have our IJK, 1, 1, 1, 0, 0, 100. Again, for time's sake, if you trust me, that gives us the vector 100, -100, and 0.